So I'm going to talk about the parameterization of lateral boundary layer eddy diffusion in ocean models with a general vertical coordinate. This work is done in conjunction with Andrew Shao, Scott Bachman, Keith Lindsay, Gökhan Dalambashoglu, and Frank Bryan. And we started working on this project when Andrew Shao visited us in September of 2019. So that's when we start putting these ideas together and writing a module in MOM6 to implement this kind of diffusion. So I want to thank Andrew in particular for coming here and helping us with this task. And the motivation for that comes from this idea of lateral diabatic eddy fluxes near boundary, which was kind of put forth by Triguier et al. In 1997. Thanks to Steve Griffin for pointing that out to me. And then later on, Ferrari et al. Kind of applied that concept, and then what they did is shown in this conceptual model of eddy fluxes in the open ocean. So in the interior, you have basically adiabatic mixing, so along layers of neutral surfaces. And then as you approach to a boundary, in this case, the surface of the ocean, the isopycnous tend to become parallel to that boundary. And then within the boundary layer, the fluxes are horizontal, so they are diabatic rather than adiabatic. So for the GM part, this has been widely implemented. MOM6 already has the vertical stream function from Ferrari et al., but for the diffusion part, it doesn't. And in POP, this has been done in both with diffusion and as well with the effective GM part. So Gökhan and others have implemented this idea in POP, including changing the neutral diffusion from being neutral to being lateral. So we kind of start talking about this when I show this first fully coupled, or one of the first fully coupled simulations that we did with CSM MOM6. So I'm showing sea surface salinity in this fully coupled run, and I have this arrow here in the Persian Gulf, and pointing that the extreme values, the maximum salinity is coming from this region. This happens in the GFGL configuration, fully coupled as well. So we have very large salinity values. It's going up, not monotonically, but it's going up with time. So when I first showed this to the group, Gökhan asked me, do we have a lateral diffusion? And then I said, no, we don't. We just have the neutral diffusion. So that's how the talk about adding a lateral diffusion near the boundary came into place. So we were hoping to, we were compelled by this follow the previous conceptual model in hoping to minimize this issue. We know that it's not going to solve the problem. Indeed, it does not solve the problem. It does minimize this issue. The problem here is also, we had to open up a little bit the Hormuz Strait to get more water flowing into the Gulf. But adding a lateral diffusion does indeed minimize this issue. I'm not going to show in the main part of the talk. I have a plot in the extra slides if someone wants to see the before and after result. So our goal is to represent the lateral diffusion of tracer fluxes due to mesoscale eddies within the boundary layers of general vertical coordinate models. And on the left, so this is the ready operator. So in Z coordinate models, that's how normally the neutral diffusion is done. So you can apply a diffusion along isopycnous or neutral surfaces, and notice that it has this horizontal lateral part in it. So for example, when this was implemented in POP, you could do both neutral and horizontal diffusion within the same operator by near the surfaces just using the 2D part of the tensor. And what we want is just this lateral part. And we need to keep in mind that the method needs to work in conjunction with neutral diffusion schemes in general vertical coordinate ocean models. And I will defer to Andrew Shao's seminar a month ago to explain the method that was implemented in MOM6, which relies on high-order remapping schemes as well as doing kind of sorting algorithm to find the neutral surfaces. So we proposed initially two methods. The first one we call layer by layer, which is a more straightforward way of doing things where diffusion is applied in a layer by layer using information only from the neighboring cells. And then we also had a second method, which is kind of a lower order representation, cross-Turner-like, if you will, where the assumption is that eddies don't care if there is a vertical gradient in tracers within the boundary layer. It will mix kind of regardless of this gradient. For today, I'm not going to show about this bulk approach. And the reason is that since I started doing more idealized experiments, I realized that the bulk approach has a lot of limitations. We need to do a lot of flux correction within that method because you might have big jumps in boundary layer between two cells, and then the fluxes are extremely large, and we need to kind of control that, and it becomes less effective. So I'm going to talk about the layer by layer method, although both are implemented in MOM6. So the way the layer by layer method works, we have this schematic. So we have a left column and a right column. The circles are the tracer points, the crosses are the velocity points, and we have 4 layers shown here. There's two isopycnals that are outcropping to the surface. And then we impose this kind of boundary layer depth. The first thing that the scheme does is go and find the indices containing the boundary layer on the 2 columns. So on the left is the index number 4, and on the right is index number 2. And then we go and calculate the diffusive flux at each layer. And the way we do using this formula, so kappa here has all the information about the grid spacing as well as the time step and the diffusion coefficient. So this comes to us ready within the module to be used. And then we use the so-called effective thickness, which is the harmonic mean of the 2 cells, and it is at the velocity points. That way, we ensure that if a cell vanishes, this is going to go to 0 and there will be no flux. And this also assures that the flux is always downgrading. For example, in this case, if left is bigger than right, is always going to be going from left to right. And then the last step, which was something that I added relatively recently, and it was an idea from Keith Lindsay during our discussion, is to have a linear decay between the minimum boundary layer depth, which is on the right column, is the index number 2, and the maximum boundary layer depth, which on layer 4. So basically, what I do is I say, okay, well, before I was stopping at the minimum boundary layer depth. So I was stopping at layer number 2, and then these 2 layers did not have flux. So now what we do is we go from a maximum at this top interface of the minimum of the layer where the minimum boundary depth is to a 0, so a coefficient that goes to 0 at the bottom of the maximum boundary layer depth. So this does like kind of a linear decay in the flux and assures that there is a flux everywhere within the boundary layer. It's kind of ad hoc, but that's the scheme that we came up with. So as I said, it has been implemented in MOM6. It is now in the main branch on Dev Master. So all people that have access to Dev Master and have merged the latest Dev Master have this module available. It follows the MOM6 code style. It is oxygenized. It has unit tests. It also has dimensional consistency testing, thanks to Bob Hallberg. And we also added the option to diagnose diffusive flux, both in 2D and 3D, as well as tracer tendencies, also both in 2D and 3D. So this is kind of a proof of concept using a very simple experiment. So the experiment is as follows. We have 2 columns, and we impose a temperature profile on the left column that goes from 20 degrees Celsius at the surface to 4 degrees Celsius at the bottom. It is 500 meters deep. And then on the right column, we do the same thing, but we subtract 1 degree. So using a linear equation of state, that's just a function of temperature, salinity salinity is constant. We end up with this isopycnal slope. It's kind of a medium slope. And then on top of that, so that's the initial condition for temperature and density. Then on top of that, we apply 2 passive tracers. So passive tracer number 1, which I call tau1, has no horizontal gradient. So lateral diffusion should be 0 here. And then passive tracer number 2, which I call tau2, is parallel to the isopycnos. So we expect the neutral diffusion will be 0 or very small in this case, because the neutral diffusion scheme is not perfect. So the resolution is 100 kilometers in the horizontal to mimic our typical 1 degree type of model that we need, this kind of parameterization. Vertical resolution is 10 meters. I'm just going to show a Z-star solutions with Z-star for now. Kappa is constant at 1,000 meters squared per second. I already said linear equation of state. Then we prescribe the boundary layer depth, and we also turn off the dynamics. There's no dynamics at all. And then I have two experiments. The first one is the control, where the neutral diffusion is applied everywhere. And the second one is lateral boundary diffusion, I call LBD, where neutral diffusion happens in the interior, and then lateral diffusion happens in the surface boundary layer. And if you look at the tracer tendency, again, I turn off horizontal advection and I turn off vertical mixing. So the only terms impacting the tendency are the lateral diffusion, the neutral diffusion, and the vertical remapping. For the control, we don't have a lateral diffusion, so it's the last two. And for LBG, all the three terms are acting. So the first problem is if I impose a boundary layer depth, it's 100 meters everywhere, as shown by the dashed line. And I'm going to show tendencies for tracer 1 in this slide. So remember, tracer 1 has no horizontal gradient. So if the top panels are the control and the bottom panels are the LBG, left is neutral and right is lateral. So for the control, we have only neutral diffusion, and we see it happens throughout the water column. Some locations do not get a flux because there is no density that's matching those on the neighboring cell. And again, Andrew showed this nicely a month ago. And it has no lateral diffusion. And then for the LBG case, the neutral diffusion, the values are basically very similar to the control case, but it doesn't happen within the boundary layer. And the lateral diffusion within the LBG, in this case, is basically round off, right? Because there's no horizontal gradient. Then for tau 2, for tracer number 2, which is parallel to isopycnos, in the control, neutral diffusion is very small. It is non-zero, but it's very small. And that's because the scheme is not perfect. I'm using a continuous reconstruction here, which is not the best we have, but is the fastest. And I wanted to keep it consistent with the global model. That's why I'm using it. So it is small, but no, it is non-zero, but small. It does not have a lateral diffusion. And then the LBG experiment, again, the neutral diffusion is identical to the control because of errors, numerical errors. And then we have the lateral diffusion being applied within the boundary layer. Now, this is problem number 2 is kind of a more extreme case where the boundary layer goes from 100 meters on one side to 500 meters, so the entire water column on the other side. And this is not unusual in the ocean. In fact, it can be even larger than that, like 1,500 meters or so. So we wanted to see how the linear transition is going to play a role in this case. Again, tracer number 1 has no horizontal gradient. Neutral diffusion in the control case is happening everywhere. And there's no lateral diffusion. Neutral diffusion in the LBG is 0 because the scheme is not even going through because it says stop right there because that's the maximum boundary layer depth and it's the entire water column and it has 0 lateral. And now tracer number 2, it's small values for the control case, 0 for the neutral diffusion in the control case, 0 for the lateral diffusion in the control case, 0 for the neutral diffusion in LBG, and then it's non-zero and it decays nicely with the LBG lateral diffusion. So this is just to show that it's doing what we want. And if you think of what's happening with the isopycnals, because here it's just controlled by temperature, the LBG, the lateral diffusion within the LBG experiment is flattening the isopycnals. So it's removing available potential energy. I apologize for the noise in the background. So now we turn it to a global ocean model. So it's the ocean sea ice. Both ocean and sea ice are active. And the experiment is done with CSM-16. So the configuration is identical to what I showed in my talk a few months ago. I'm using mount 6 and size 5 with GRA 55 forcing. Sorry, let me close my window, see if that happened. I'm using a nominal 2/3 degree grid spacing with equatorial refinement, a Z-star coordinate system with 63 layers. Vertical mixing is via CV mix, GM and ready are controlled via Mickey geometric. And again, I'm referring to my talk a few months ago for a complete description of this configuration to save time. And I want to emphasize it does not have all the whistles and bells that we want. We're still actually working on this configuration. It's changing pretty much every week. The two experiments I'm going to show are basically the same as in the thought experiment. I have a control case with neutral diffusion throughout the whole water column and LBG, what I call LBG, which has neutral diffusion in the interior, lateral in the surface. And just to make sure everything else is being turned on now. So we have all the diffusion and advection and stuff. So it's different than the thought experiment that I showed before. Looking at mixed layer depth, so this is the density criteria, the 0.03. And I'm averaging, so this winter time, I'm averaging over the last 20 years of the simulation. It was run for just one cycle. The left is the control, the right is the de Boer climatology. We see that the control overall has the main locations where we have deep mixed layer depths. We perhaps are missing some on the Southern Ocean and some extreme values here in the Nordic overflows. And then on the bottom left is the LBG experiment. If we compare both control and LBG, visually we cannot see anything. We have to do a difference, which is what I show on the bottom right panel. And here should be D, not C, sorry. So this is LBG minus control. And we see that locations where tend to have deep mixed layer depths become deeper. So it's deepening the mixed layer depths with the lateral diffusion. And there's some locations where it also becomes shallower, but it's overall deepening. And this happens where you have the largest gradients in mixed layer depth. And it's on the order of like 20 meters or so. Some extreme values reach 120 meters. The same for the summertime. Again, we're overall capturing the structure, but we're missing some extreme values in the Southern Ocean. And the lateral diffusion enhances locations where you already have a deep mixed layer depth, as shown here, but is much more localized in the summertime and is also much smaller. It's like half of the increase in mixed layer depth. Now looking into polar heat transport. Again, this is mean over the last 20 years, and I'm showing the global contribution from each component. Advection at the top, neutral diffusion in the middle, and lateral at the bottom. Notice the change in the Y scale between these plots. It is much larger in the advection dominates, and we cannot differentiate the two solutions by looking at the advection only with this scale. They're on top of each other. In terms of neutral diffusion, we start to see a slightly difference. The control case has slightly stronger southward in the Southern Ocean region. We can see a little bit here in the Northern Hemisphere too. And then the last panel is the lateral diffusion, which is kind of a third of the neutral diffusion. And again, contribution is small, but we can see here that it is doing something. And then when we look at the sum of all the terms for the global polar heat transport, it is slightly better in the LBG. So LBG is in orange, control is in blue, and on the background I'm plotting the GRA 55 from Sohino et al. So this is using the forcing as a way of estimating the polar heat transport within the first cycle is the mean plus minus 1 standard deviation. So the lateral diffusion is acting towards improve the solution, so towards agreeing better with what it should be. But it's very small contribution. For the AMOC, I'm not going to show the stream function because it's impossible to differentiate them visually. Rather, I'm going to show some AMOC time series at 26 north and 45 north. Again, blue is control, orange is LBG. For 26 north, in both cases, they're very similar. For 26 north, if you do the average, is slightly stronger. For the 45 north, there's basically the same on the average along the first cycle. So it's the same idea. It's improving slightly, not clear in 45. My experience and what I've been told, it takes longer to see the effects at that latitude. So we probably need to integrate the model for a longer time. And then finally, in terms of global mean potential temperature, we have that lateral boundary diffusion tends to slightly cool the ocean. So it's a short simulation, just one cycle, and we already see this slightly difference between the global mean potential temperature between the two cases. And the reason that's happening, so now I'm showing the mean net surface heat forcing. So this is average using monthly mean over the entire simulation. And the net heat forcing is all these terms. And we see that overall, I'm showing the difference between LBG and control. So overall, LBG has less heat being imposed. And this is because we have both latent and sensible heats that are a function of the state. So this turbulent heat fluxes are a function of state. And we see that the differences are occurring in the regions where we have the deepening of the mixed layer depth. So this is acting to, through the difference between potential temperature in the ocean and in the atmosphere to reduce latent and sensible, and therefore the LBG run is slightly cooler, it has slightly less heat. So just to summarize, a method for applying lateral diffusive tracer flux due to mesoscaleris with thin boundary layers have been implemented in a general vertical coordinate ocean model, MOM6 in this case. We show a proof of concept using a two-column case, as well as we tested in a global ocean, ice ocean experiment using CSM MOM6, in both cases using Z star. Adding the lateral diffusion in the surface boundary layer overall leads to an overall deepening of the mixed layer depth, and therefore a small reduction in the total ocean heat content. And although the impact on climate-relevant metrics such as polar heat transport, MOC, and so on is not substantial, the solutions are overall going towards the right direction. There's still a lot to be done. This is a few things that we have on our radar right now. First one is to test this new method using additional vertical coordinates. I've just shown Z star. I'm currently working to at least demonstrate that it works on additional vertical coordinates such as rho, hybrid, etc. We plan to enable the lateral boundary diffusion in the bottom boundary layer, and that's something that Andrew Shaw is going to lead. And we also plan to add the ability to prescribe a three-dimensional tracer diffusivities rather than two-dimensional, which is what happens in MOM6 right now, is just constant in depth. And all this work will be done as part of our EDDI CPT that's currently happening. And that's all I have. I'm happy to take any questions.
Steve, go ahead.
Yeah, thanks, Gustavo. I wrote a couple of questions in the chat. I didn't know if we'd be able to get to it, but I think you answered the first question, namely you're only testing Z star. If you had, say, a terrain following coordinate that was in the boundary layer, are you going to rotate to be horizontal, or are you going to just continue to diffuse along the coordinate surface?
We are just going to diffuse along the coordinate surface. So the indices, not the true horizontal. That the scheme is working based on the indices, not the true horizontal.
Okay, so the second question is, what is your criteria used to determine the boundary layer thickness? Is it just coming from KPP, for example, your boundary layer scheme, or do you have additional criteria? In particular, in a paper from NCAR folks with Large et al. 1997, there was a proposal to define a EDDI vertical length scale, which is proportional to the Rossby radius times the slope of your isopycnal. And that was used in MOM5 days to couple to the KPP boundary layer to give you a effective boundary layer thickness over which you would taper your scheme towards zero. Are you thinking about that sort of?
No, thanks for asking that. We are not thinking about that. The way it's happening right now is just coming from either KPP or EPBL. We have the option to do both boundary layer depth, use both boundary layer depths. But this question of using something that's more, it has constraints using eddies, mesoscale eddies, it's a good question. We haven't talked about that, and maybe we should at least mention, explore the differences. Thank you for asking.
Great, thank you. Just to remind you, that is an in-car paper, so you might want to get your in-car colleagues to remind themselves that they were part of that paper.
Yeah, no, I'm aware of that paper, and I'm sure they will ask me on the next meeting about it too.
Thank you.
Thank you.
Okay.
But I would add something. I mean, this idea of a boundary layer depth, it's pretty nebulous, you know. That's why one scheme gives a different answer than another. I mean, it's quite clear if you just have surface forcing in an idealized situation and everything stops at some level and there's lots of stratification. But if you got the real ocean and there's mixing from below and forcing from both sides, it's a little nebulous what it is. I mean, it's just, so I wouldn't, you know, really know what to do exactly.
I
To
agree.
be perfect, you know.
Yeah. Yeah.
But
so,
you're not having huge differences, so
Right.
anything will probably do.
Yeah, that's the point. It is not affecting much, but it is affecting on the right direction. And until we come up with a better scheme, I think that's we can go forward with that.
Bob Hallberg.
Thanks, Gustavo. That was a nice talk. Everything you talked about today was for the surface boundary layer, and the surface boundary layer is pretty flat. But you also said that you're thinking about applying the same sorts of ideas for mixing along a potentially sloping bottom boundary layer. Do you envision that there will be additional constraints that you have to apply so that the energetics associated with mixing along a sloping bottom boundary layer don't act as a large source of mixing of energy to the system as a whole in a way that wouldn't pertain to a essentially flat surface boundary layer?
Yes, that good question. Thanks, Bob. We are thinking of a different way of doing it. So Scott Bachman has thought of a way of doing this within the neutral diffusion algorithm. So adding kind of a pressure dependency on that scheme that would allow to make the scheme works purely horizontally or like along a constant pressure surface. The thing is that the neutral scheme, as you know, it's very hard to work with, and we need to spend some time and implement this idea, and that's what we plan to do in the future. So everything is going to be, there's not going to be a separate module that does that. Everything's going to be done within the neutral diffusion, and then we hope we will be able to accommodate for a sloping boundary and make sure that the flux is parallel to the boundary in that case.